Okay, let's get started. Good morning, good afternoon, good evening. Welcome everyone to our next episode of the YugabyteDB Friday Tech Talks series by engineers for engineers. It's always nice to see some regular attendees, as I can see from the LinkedIn comments. So welcome back everyone. And my pleasure to introduce to you today's speaker, Piyush Jain. Piyush, why don't you get started,
Mhm.
perhaps both by introducing yourself and what you do at Yugabyte, and then jump right into the topic for today.
I'm a software engineer here at Yugabyte, working on the core DB, uh, and working on a few interesting things. We can discuss those. So that's in short about me.
Yeah, I mean, I guess you have been working a lot on the transaction subsystem and how it interacts with the language or the SQL layer of Yugabyte, and that's the topic for today. So yeah,
Mhm.
jump right in.
So I'll jump in by let me share my screen and let's see. So I had this deck here today. We'll use this. Let me get rid of this. So we'll discuss isolation levels. Now, before we go into what isolation levels are, right? Actually, before we go into that, let's discuss the why of isolation levels. Why do we even need to discuss this, right? So any database would want to allow multiple concurrent transactions to be running simultaneously, right? And that's because let's say you're a customer for a bank and you want to transact. So you don't want to wait for two other strangers transacting. Like you don't want to wait for them to transact to make your transaction. You don't want to be blocked. So you certainly want to allow more transactions to occur concurrently in a database, right? Now, when you do that, uh, what happens is things become a bit tricky when you want to allow multiple active transactions which are trying to update different pieces of the database, different uh, rows of a table, things like that, right? So that brings in isolation levels as to how do you want the database to behave uh, 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 when you have multiple concurrent transactions, right? So that is the why of why we have isolation levels, right? Now we'll go to the simplest one first, which is serializable. And what this means is, even though a database tries to do concurrent transactions, if it is serializable, it means it would behave as if all transactions were executed one after the other, right? In some serial order. So you would see the database as if it's doing one transaction uh, 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 after the other, right? As if like without anyone blocking you, like your transaction. So that is serializable. Now, if for some reason the guarantee breaks, right? That is, the database is not able to serialize your transactions, then it is going to throw some errors, right? So those are serialization errors. Now, what I've listed here is isolation levels in Postgres. And we have three of these here. Now, I explained serializable. Let me, use an example to really drive home the point of, um, what are the cases in which you can't serialize transactions, right? Concurrent transactions. So let me, uh, so I have a database instance here. I have two connections here. So what I'll do is I'll create a table first, right? This table is a simple table where you have some doctors and you have some field which indicates whether the doctor is in office or not, right? And let's say we had four doctors here, all of them who are in office. Now, if at all there's a system which wants to execute two transactions which allow a doctor to go out of office, right? So just set this field to false for some doctor if there are greater than equal to two doctors in the office. So the constraint is we want some doctor to be in office at some point in time always, right? So what happens is, as database users, we might, there might be two users starting transactions. serializable transactions, right? And they want to, send two different doctors out of office, right? And uh, they could do something like, get the count of doctors in office, right? And let's say they get the count of doctors. So,
Piyush,
Mhm.
there's one request, if you could make that font size a little
Oh,
bigger.
yeah, let me do that. Is this better?
Yeah, that's much better.
Mhm. Okay, so uh, let's assume this guy who's running this transaction wants to send doctor one out of office. So he or she is just going to do this, wherein set in office to false for doctor ID one, right? Now another user might want to do the same for doctor two, right? And actually here I have four doctors. So let's assume you want greater than equal to three doctors in office, just for the example, right? You have different sort of physicians,
Sure.
surgeons, right?
Mhm.
So you want greater than equal to three doctors in office. Now, if they were doing this sort of thing wherein they get the count in their app, they check, hey, is the count, you know, greater than equal to four? If so, I can just remove one of the doctors. So if they do that, uh, uh, these two transactions should not be able to execute, I mean, commit together, right? That would result in, they seeing a count of four and sending two doctors out of office, which is wrong. And if the transactions were to occur one after the other, like in a serial manner, one of them would eventually be aborted, like stopped from execution, right? So if you see, this is what happens. You see a conflict here, and that is just because these two transactions can't be serialized, right? So yeah, this is to just drive home the point that if you do concurrent transactions, you might result in bad states, which you might not expect. So this helps avoid that, right? Uh, let's move to the other two transaction isolation levels. So uh, 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 a precursor to that, like why these two even come to existence, right? So serializable is complex to implement, simple to understand. It has performance penalties, right? So there are many apps which might not need serializable isolation level, and they are okay with weaker semantics, and they can handle stuff in their app, right, to get the performance benefit. So that's why we have these two weaker isolation levels, right? And these only dictate, uh, what one transaction can see in its lifetime. Basically, how are transactions isolated from each other? What can one transaction see of another transaction, right? Can it see all dirty writes, that is things that have not even committed, or can it see just committed entries from other transactions, things like that, right? So I'll go on to explain read, like repeatable read, quickly. So this is basically snapshot isolation. We also call this snapshot isolation. So what we do here is every transaction is going to run off a single snapshot of the database. So when you start the transaction, you take a snapshot of the database, like a read point or something, and everything in the transaction is going to see everything as of that snapshot and whatever it has written, right? So that is basically snapshot isolation, which is repeatable read. So you can read your own reads, and if you haven't written something, you can do repeatable reads. That is, reads are going to match, right? So one good fact about this is that readers won't conflict with writers, and vice versa as well. So that's a good quality of repeatable read. So only writes conflict with writes. I'll show that in a minute. Yeah, and again, this is possible because Postgres does MVCC. So you keep multiple versions of the same piece of data, and this is easy to implement then, right? So let me actually go on to show uh, repeatable read, right?
So,
Again, one more thing.
Piyush,
Hmm?
Piyush,
Yeah.
would it be interesting to show in your same example
Hmm.
how if you switch to repeatable read, it would allow both doctors' state to be changed and the count to get less than 3. And why some cases need serializable, but maybe it would be interesting if you just
Makes
did the
sense.
begin of this transaction in repeatable read mode.
Let's do that. So let's say I do.
Oh, your count is already 3 actually right now.
That's okay. Let's assume we don't want the count to go
To
yeah
to,
to 2.
to 2, let's say. Yeah.
Oh no. Let's say we want it to go to 2, but not 1, right? We don't want 2 more people to go away. Yeah.
Yeah.
So I'll just roll this back. Again, I say Postgres here, but we are doing all of this in Yugabyte. It doesn't matter because it's the same semantics, right? So use Postgres, use Yugabyte, it's the same. So what we'll do now here is, as you said, let's update Doctor 2 and send him out of office, right? And let's.
But
So
the
actually
count,
update is wrong.
the point is that the count that
Yeah,
you
let's
want
do
to
a
get the
select.
counts before.
Yeah. So let's do a select. So as a user, I see 3 and I'm allowed to send one person out of office. The same here, right? Now, I as a user want to send Doctor 2 out. I do that. And I send Doctor 3 as well out, right? And then we commit. Now both are allowed to commit. That's because there are not different, I mean, there are not some snapshots, but they touch different pieces of data, right? So they don't really conflict. And this is basically the weakness of repeatable read. So if you expect things, I mean, if you expect things to work as if transactions execute one after the other, you won't see that here. And yeah.
Yeah, I think the point to reemphasize is with repeatable reads, read set and the write set conflicts are not detected, right? And in this case, the two transactions had different write sets. Their read sets did conflict because they both depended on the fact that the count was 3.
Yeah.
But repeatable read doesn't catch conflicts between the read set and write set. You need a write conflict. But in spite of that, for many applications, it's still an overkill because write conflicts are the more common use case, and repeatable read is very useful in practice because of the other point Piyush mentioned, that with repeatable reads, essentially, once you have multi-version concurrency control, readers don't even need to take locks, and it's just so much faster in terms of performance. Go ahead.
And actually, that brings me to another point which I realized. So there are workloads. For example, there's this TPCC benchmark, right? And if you see that, that runs, that gives serializable semantics, even if you run with repeatable read. So the workload is such that they don't even need, all the checking of serializable. They are by default serializable, right? They have it all in the workload itself. Yeah. So this might be useful for many people if they want to get performance. Now let's go to another isolation, which is the weakest, which is read committed, right? Now, what happens in read committed is we get a new snapshot. We take a new snapshot for each query in the transaction, similar to repeatable read, but the snapshot is per query now. So I execute some statement that's on some snapshot. If I execute the next statement, it's going to see a new snapshot, right? So it's going to include more transactions which executed in the interim period, right? More committed transactions. So that's one thing. The other thing is you don't see serialization errors ever in read committed. So you won't see conflicts. And how Postgres handles that is, it is going to, if there's a conflict, right, it is going to reread that row or tuple. And that will be based off a latest snapshot, and it is going to do the update, right? So what essentially ends up happening is, if you have a statement which updates like 3 or 4 rows, and let's say you see a conflict in the 4th row, so you do the update for the first 3 on some snapshot. For the 4th one, you use a different snapshot just to avoid the conflict, right? And that's how read committed avoids conflicts. So it's an even weaker isolation. And let me show this with an example, right? Let's use an example. So let's see. everything is committed. This is fine. So what I'll do is I'll pick a new table for now. So this is a table with a primary key and two columns, right? V1 and V2. So I insert a row here, 1 comma 1 comma 1, right? And let's do, actually, let me do one thing. I'm changing the example now. So let's do this where we have two rows, right? And let's say we are doing read committed. So I start a read committed transaction on both sessions. Now what I want to do is I want to update V1 to 6 where V1 greater than equal to 1, right? So essentially I'm trying to update both of these rows
Okay.
to the value 6, right? So instead of one row, I'm updating two rows. And let's do something different here, which is let us update it to 7 um, where k equals 1. So I just, or let's say k equals 2, right? So this guy is updating v1 to 6 on both rows. This one wants to update it to 7 just for the second row, right? Now, if you do this, right, it waits. It waits because it wants to write a conflicting entry. I mean, it wants to do a conflicting update. Now, as soon as I commit this, right, what happens is this transaction goes ahead, makes the update, and let's see the result. Yeah, so you see, this was, so what essentially happened is as soon as you make the commit here, this transaction is going to reread the tuple k equals 2 and it will update that, right? So yeah, that is what happens here. Now I should mention a few things. We could see
And
waiting behavior here, right? Go on.
and maybe to clarify the reread, instead of v1 equals 7, you could do something like v1 equals v1 plus 10, and make sure that you're
Oh,
actually getting the new.
yeah, actually, yeah, I was thinking that could be a better example. Yes. So let's do that. I set it to 6 again here. Let's do v1 plus 5, right?
Yeah.
And let's say commit. Actually, let's not commit. Let's just select here in the transaction, right? Yeah, so it does 11 now. And if you see it gives 6 here. Actually, it was 6 here as well. So, I mean, this was a no-op update sort of, but doesn't matter. We can see that it takes the newer value, right?
So Piyush, I think you're also demonstrating one other aspect here. Essentially, the read committed also
Yeah,
is able to do pessimistic locking and
pessimistic
wait as
locking.
opposed to optimistic and give up early.
Yeah, so as you could see here, we were waiting, right? So what this, I mean, we call it pessimistic locking, but this is essentially waiting behavior, which is if there's another transaction doing a conflicting write, or which has already done a conflicting write, and you can't make progress, right? So we just wait here in anticipation that the other transaction is going to either commit or roll back, do something. And once that happens, we can make progress, right? Based on whatever happened. Like, so this waiting essentially, so this is a Postgres semantic actually. The other way to do it is, don't wait, just abort your transaction or the other transaction. That's called optimistic locking. Now, either methodology either methodology is going to be like better for some workloads, but here you could see pessimistic locking, which is yeah. So this is Postgres semantic, and we want to match Postgres as much as possible, right? So hence you see that. Yeah. So again, if we go back here, Yugabyte has all three isolations now, all three which you can see in Postgres. Now, serializable, it's the same as what you see in Postgres, the strictest semantics. So not much difference there. Read committed is new, and it matches the semantics in Postgres, read committed, except a few caveats, which I'll get to, right? And then there's a repeatable read. Now, I want to mention one difference between our repeatable read and Postgres' repeatable read, it's a beneficial difference. It's no drawback, right? So uh, in in YSQL, we take finer level locks, right? So if you have a row with multiple columns, and if you're updating some columns, you just take locks on those columns. You don't lock the whole row like Postgres does. Now, this allows multiple writers to update different columns of a row, which is more concurrency, right? Which is much more better. So let me just demo that actually, that beneficial difference. And let's clear this. So I'm doing repeatable read on both sides. I'm not sure how to hide this. Let's move it. Okay. So we still have the table with 3 columns, right? And what I'll do here is I'll update V1 on the first transaction. I'll update V2 on the second transaction, right? 2 different columns. And you can see both of them go through, right? Both of them go through. Now, if I were to do the same on Postgres, I have Postgres as well here, right? So,
And if you could
okay, I
just make
already
the
tried
font
this.
a little bigger here.
Yeah. So I already tried this before this meeting, I guess. But let's do it again. So let me not drop.
Yeah.
Let's see what there is. Yeah, the table is there. So what we'll do is repeatable read on both sides. Now update this column here, V2 on this side. You see blocking. Now this is pessimistic locking in Postgres. Basically, if I do a conflicting write, I block. Right. If you do a commit, now this guy is in anticipation that if T1 either fails for some reason, I'll make progress, right? But the anticipation is useless because we committed. So you see a conflict. So you have to retry the whole transaction, right? Now this is more of a problem if you have long running transactions, things like that. So yeah, this was one beneficial difference in our repeatable read. Now let's see. Let's move
There are a
ahead.
few questions, Piyush, and you can, some you may be addressing along the course of the talk. One is like, what challenges did Yugabyte face in implementing these isolation levels and how were you able to overcome them? And another one was, um, is there kind of a timeout for waiting for these pessimistic locks?
Okay, I'll answer both. So the main difference, so Yugabyte doesn't just have to implement these isolation levels and match the semantics of Postgres. The added difficulty is that this is a distributed system, right? So when you have a distributed systems, like it's harder to do transactions. Your clocks might be out of skew, and when that happens, it's not just about isolation. There's also the orthogonal axis of consistency, right? So for example, I mean, actually there's an example which is going to come ahead wherein I'll explain read restarts. But the main takeaway is the difficulties in implementing this for a distributed database, right? Yeah, and
Yeah, I
handling
think we can
clocks.
cover that during that your
Yeah.
slides later. Yeah.
Mhm. And is there a default timeout for waiting on a pessimistic lock? Yeah, so we use the same timeout as the statement timeout. So if let's say like the statement timeout is 100 seconds, we wait for 100 seconds and then that's it, we give up. So
And presumably it's not busy polling. It's what kind of a model do we have? If you
yeah.
could clarify that.
So again, this is not busy polling. It does polling with exponential backoff, right? So this is Postgres. Let's go here. So whatever waiting we do here, it's basically exponential backoff polling.
Got it. And is there some plan to make it more based on like a notify mechanism instead?
Yeah, so this is going to come soon in the next bleeding edge release, which is the next preview release. I think 215. We'll move
Sounds
to
good.
a signaling mechanism, so that will be more faster, right?
Sounds good.
And we'll save resources as well because we don't have to pull less compute, right?
Yeah.
So actually, moving on here, there are a few more points which I wanted to cover for read committed with the example, but let's move on actually. So I already mentioned this, which is, we take a new snapshot per statement in the transaction. This is Postgres behavior. We have pessimistic locking built in via the polling, exponential back of polling, right? Now, the main takeaway is there are many people using Postgres who use the default isolation, which is read committed. And in Postgres, you don't see conflicts, right, with this. So we do the same as Postgres. We don't throw conflicts. We handle it internally by, rereading the row, etc., things like that. Now, there's another class of errors, which is read restarts. Now, this is something which only can be seen in distributed databases. It only comes up when you distribute the database. It's a problem inherent to distributed databases, not just Yugabyte, right? So the thing is, in Postgres, if you don't see serialization errors with read committed, people also expect that they don't see read restart errors, right? So we handle that as well. So if you use read committed, you won't see these. You might have seen these earlier in repeatable read. I'll explain what these are exactly. But moving on, yeah, this is just the usage, how you can use this on a Yugabyte cluster, be it 212, 213. Both of them have this. So earlier, read committed was mapping to repeatable read in Yugabyte. That's because we didn't have read committed. Now, if you want to use read committed, like the syntactic read committed in YSQL, if you want to map it to the real read committed, you just have to turn this flag on, right? That should get you going. So let's move on to read restarts. Yeah. So this is the interesting part here. So most people have seen this at some point with Yugabyte. Let's declutter this, right? So let's say we have a cluster of nodes. I've just shown 5 nodes here. Now there's some real time in the world as we speak. It keeps moving ahead. There's some real time, but computers use some physical clock, right? And when you have multiple computers like systems, you can't synchronize the clocks easily, right? So all of them have their own perspective of time, and it keeps increasing monotonically on each node, right? So in this system right now, what I'm showing is you have these nodes, and if you see uh, these 4 nodes see time as 5. I'm just using an integer to make it easier. 5 is the time on these, and this guy says that the time is 2, right? And let's assume we are in a world where the max clock skew between nodes is 8. So I mean, there could be another node with time as 10 in its perception, but it can't be more than that because this is 2, and it goes the other side as well, on the left, like the negative side, right? uh, and again, when I say max clock skew is 8, all all cloud providers or all systems usually have this NTP synchronization or some mechanism to limit the clock skew between nodes, right? Because clock skew is it makes distributed algorithms harder to implement, right? So assuming we have a clock skew of 8 units, let's assume there's a key value pair, k equals 1, v equals 1. K is the primary key, and it was written as of time equals 0, right? And this is the raft group for this for the tablet which hosts this key value pair, right? And let's assume n1 is the leader, right? So given this system, let's assume some user connects to n5, like YSQL on n5, and tries to do a write. So the write is going to update the column v to 5, right? And the write happens at t equals 5 as part of some transaction, right? Now, this is going to be a provisional write at t equals 5. So I'm not showing it here. It's a provisional write. It's somewhere there. Now, clocks move. So the real time moves ahead by 2 units. Clocks also bump up by 2 units everywhere. And the user commits at t equals 7, right? So if the user commits at t equals 7, the provisional entry gets written to the database forever with k equals 1, v equals 5 at t equals 7. And remember, we are MVCC, so we store all versions, right? We store a timeline. So this is the state now. We wrote this, fine. Everything is fine. Now, let's assume clocks tick 1 unit ahead, even further. And so let's assume now that this user gave a phone call to another user in some other part of the world, right? Because this is a geo-distributed database. Let's assume, right? So user one gives a call to user two that, hey, I wrote v equals 5. You can just go ahead and read. You should see the same, right? So this guy goes in, connects to N4, does a read. Now, when the user does a read, the timestamp on the node is t equals 5. So the read is just going to pick some timestamp, right? The latest timestamp that it sees. It picks t equals 5. Now, if you use t equals 5, you essentially won't be reading this row because this is in future, right? So now you don't know. So this is incorrect behavior basically because this t equals 5 makes you not read this row. But the thing is, this t equals 7 is actually in the past. It's just that it's 7 because of clock skew. So some other node which wrote stuff in the past had a timestamp which was ahead. That's it. So you really want to read this row. You don't want to miss it. But now there could be a flip side wherein it could be that all clocks are in sync, luckily, and you really don't want to read this row. That is, your transaction could have started like long ago, and this is really a new entry. You're not supposed to read this. This is not part of your snapshot. So there's this flip side as well. So given this, you're stuck in this ambiguity whether should I read this row or not, because you can't really figure out as to the node which wrote this, was it ahead or behind my clock, etc. You can't do that easily, right? So you're in this ambiguity. So just to not give the user the wrong result, we throw a read restart error, right? So this read is not going to succeed. You get a read restart error, and the user has to retry. Actually, having said that, the user doesn't have to retry always, because we have a lot of mechanisms internally to ensure that we somehow handle this on our own as a best effort. I can go into those, but let me pause here actually.
Yeah, in the interest of time, I think it suffices to say that I think there was a question also, like, is there a way to avoid read restart? Is there a way to avoid these errors? But the reality is these errors are part of the, due to the distributed nature of the system. And like you said, internally, there are many cases where we automatically handle this and retry the operation internally. But also, like you earlier said, with read committed, this error doesn't happen. Because we are able to do the automatic retry pretty much in all cases. So I think we should keep moving on because we're a little tight on time. Maybe let's get to that. Yeah.
Okay. Yeah. So moving on. I mean, this is just one use case I wanted to mention, wherein so there's this company called Temenos. They create banking apps which other banks can use. Now they ran some tests wherein they used Yugabyte for their transactional layer, and they were using read committed. So that was that, and they got some good. I mean, they got some good performance, right? So they had, like, as you can see, 39 nodes, fairly large cluster, and they could do 350 k reads per second. These are database reads, and yeah, I mean, there's no other type, right? And there's 80k writes. So actually, database reads means like, they went to the source of truth. There was like, this doesn't include reads which go via cache or things like that, right? So and there's 80k writes. So I mean, this is just to show that uh, read committed has been stress tested, sort of. So I mean, yeah. Moving on actually. About the roadmap and why I put this image. So the idea is that Yugabyte's YSQL should behave as if Postgres, And the vision is that any user should not be able to distinguish between Postgres and Yugabyte, right? It should seem as though it's the same, even though Yugabyte has all these niceties of being distributed, taking care of all of that, so resilience, availability, etc. So that's the grand vision here. And I just want to share some items that we have. So we already have read committed as a beta feature right now in 2.13 and 2.12. The plan is to, so there are some limitations with read committed, right? Um, uh, like I have listed them here. I can go into these. Now, so limitation two is like, it won't mostly affect OLTP workloads, but I've just put it here. And it's also configurable. There's easy ways to get around this. Nonetheless, the plan is to solve these limitations and GA this in 2.14, right? Yeah, that's the plan. And then apart from this, we'll have improved pessimistic locking coming. Now this will be beta into 15. Now, when I say improved pessimistic locking, let's dissect this further. So read committed already has pessimistic locking by retries, right? We already have that. Now, the improvement is that instead of doing exponential back of polling retries, we'll do a signaling mechanism. So it's going to be more faster, less resource intensive. And the next thing is we are going to detect distributed deadlocks, right? So if you have multiple transactions waiting on each other, there can be deadlocks. We don't want that. We want to detect them and abort some transaction to make progress. Postgres also does deadlock detection, right, to handle this. So this is going to come with the improved version. Now, in the current pessimistic locking version, we don't detect deadlocks and we rely on statement timeouts to avoid deadlocks, right? Because the deadlock detection algorithm is not yet in 2.14. So these are the two things. Now let me move to the third item, which is the pessimistic locking semantics that you see in read committed are going to be visible in repeatable and serializable isolation as well. So that's a third thing, and this will get us even closer to Postgres, right? And I mean, this is clearly visible, which is we want to make read committed default like Postgres. So we are considering this, right? There's a GitHub issue for all of this, all compatibility stuff, etc. So I'll stop here, pause here for questions, anything, or
I think we answered all the questions. Maybe if you want to take 1 minute to maybe contrast with the approach that Google's spanner database has taken with respect to clock skew.
oh yeah,
Yeah,
that's a good point. So Google Spanner, so they have true time, as we know. So what happens is with true time, you can get time with an error bound, like a very small error bound. But okay, that's irrelevant. So they use true time, which is fine. The thing is, to solve the same problem, they do what is called as a commit wait in transactions. So basically, in each transaction, before you commit, you're going to wait out the skew, right? So for example, I did a commit here, right, at t equals 7. So I wouldn't immediately write it here. I would wait out till t equals 15, right? And then I would write it here with k equals 1, v equals 5 at t equals 15. So that essentially solves the problem, because guess what? When you come here, uh, I mean, your timestamp would be much. So wait, hold on. If you commit wait and you write at t equals 15, it's definitely true that the clocks have moved ahead by 8 units, right? So this would have become 12, for example, right? This would have become 12. And now if you do a read, it's okay, right? You don't have to read the stuff at t equals 15.
yeah. I think fundamentally the trade-off is that in spanner, the right path waits out the clock skew.
Yeah.
Pretty much for all transactions.
Yeah.
Whereas here, that without atomic clocks and true time, waiting out in practice the larger clock skew of 100 units and so on isn't 100 milliseconds isn't really practical. So instead, the
Yeah.
design, which actually has some benefits, is rather than every write wait out clock skew, only reads that potentially fall in that uncertainty window have to wait out the clock skew,
Yeah.
which is a much rarer occurrence in practice. And it's only relevant if the read immediately comes for a record recently written. So this is a pretty reasonable trade-off to make.
Yeah. Yeah, that is one thing which I was getting at, which is exactly true. So we don't have
Yeah,
to pay the performance penalty for all writes.
yeah.
Yeah. Mm-hmm.
Okay, we are 10 minutes over. I'd
Okay.
like to thank everybody on the call who joined and for the questions. And please do join us next week for another interesting topic, which is table partitions. So this one is not the partitioning. Sometimes we refer to, sometimes partitioning and sharding get mixed up. So next week's topic is not about sharding tables into tablets and distributing it. It's really about a feature that Yugabyte inherits from Postgres itself, which is about the ability to partition tables logically into sub tables, if you will, by list or by range and so on. So interesting topic. Join us next week for that. And over to you, Piyush, for your final words.
Yeah, I mean, join our Slack channel for anything, and feel free to ping on the community Slack, for any questions related to isolation levels or transactions, anything at all. Yeah, happy to take questions, discuss anything. Mhm.
Great. Thank you all. Have a great day and weekend.